Okay, now let's quantify some of the things we can solve for and analyze on an object in vertical circular motion. So let's find for point A, so remember point A is the lowest point, the beginning of the vertical loop. We're going to find the angular velocity, so this is my omega. We want to find the centripetal acceleration, a sub c, the tangential acceleration, a sub t, and then the normal force and acting on the cart at point A. So to find the angular velocity, remember that we were given that the linear speed at A is 25 meters per second, and the radius of curvature for the loop is 10 meters. So recall from earlier the relationship between linear speed and angular speed or velocity for an object in circular motion. And this is right when the track begins to curve. So I can solve for omega by taking my linear speed and dividing by my radius. So 25 meters per second divided by 10 meters, and I get the meters cancel out, so I'm left with 2.5 radians per second. Remember, radians is just the ratio of distance to distance, so it's unitless. All right, what about the centripetal acceleration? Now I know that it begins its upward curve, so it must have some AC, and that's dependent upon the linear speed at that point squared over the radius. So notice too, since this is VA squared over R, and this is VA over R, if I take omega and multiply by V, I will get A sub C. So since this is V over R times VA. So we take our existing omega, we multiply by 25 essentially, and now we have a meter squared over a meter and a second squared, so this gives us our units of meters per second squared, which will be 25 meters per second, or 62.5, I'm sorry, meters per second squared. So this is the centripetal acceleration. We can determine it if we know the linear speed at that point and the radius of curvature. Now, what's the tangential acceleration of the car at point A? So tangential acceleration will exist when we have a net force in the tangential direction. Now, we're neglecting friction and air resistance here, so we might, in a reality sense, have some friction and air resistance causing the cart to slow down at that point. But if we can neglect that, notice that we only have a centripetal and centrifugal force. These are only in the radial direction. So without any forces in the tangential direction, we would say the net force T is equal to the mass times the acceleration in the tangential direction. If this is 0, then this is 0. So AT is 0 because we have no forces in the tangential direction. Okay? Then, for D, what's the normal force of the car acting at point A? So if I want to find the magnitude of the normal force, I'm going to apply Newton's second law. So just like we did in the dynamics unit, the only difference is now our acceleration at point A is a centripetal acceleration because it's beginning its curved vertical path, vertical loop path. So we can apply Newton's second law and say the sum of the forces in the centripetal direction, which is the same as radial. If you want to say sum of the forces in the radial direction, if you're more comfortable with not switching up that terminology, it's the same idea. It's going to equal the mass times the acceleration in that direction. Well, we already know AC here, and we know the mass of the cart. Remember, the mass of the cart is 500 kg. So all we need to know is what are the net forces acting on the cart at point A. And at point A, we have normal force acting inward towards the center of the circle, up on the cart from the track, and gravity opposite that. So for the purposes of solving this, if I call my AC as positive inward, I'm going to say normal minus mg is equal to m times AC. So if this is positive, I'm calling this positive and this negative. Now you can solve that with it in the opposite direction. So if you call this positive and this negative, you have to call AC inward as negative. You got to be consistent with that. So to solve for normal force, I get the normal force is equal to m AC plus mg. So this will be the mass times AC plus g, which will be 500 kg times 62.5 meters per second squared plus 9.8 meters per second squared, which will give me a overall normal force of 36,150 newtons. So in a circular motion problem such as this with a vertical circle, when you want to find values of the individual forces, we're typically applying Newton's second law in the direction of the force and seeing how we can use the known values of the linear speed, radius to find AC, and then solving for the normal force.